Welcome back to grade 12 graphs of motion. What I want to do in this one, I want to do a fairly substantial example. I'm going to do initially just a recap kind of approach, but let's just examine a graph like this. Let us say they give us this graph here, right? And here we go, and I've got it on blue. I don't normally start there, so let's put it back. Let's say they give us this graph. And they tell us that this is a V versus T graph. And for example, they say this is 2.5 seconds. Oh, just a hint. Please note that when you get these graphs, check on the x-axis that the times given are the coordinates of that point. Be careful they don't give you a point and then a time in between. In other words, let's say they've got this where you've got a T here of 1, let's say point A and point B, and they tell you 0.5 and point C 1.5. Obviously that is at T 0, 0.5 and time 2. Okay, very important that we that you just check your axes. Doesn't take long, but just make sure you've got the axes right. Okie dokie, what am I going to do now? Well, they give us this graph and they say to us the above VT graph shows the motion of an object launched vertically upwards. Using the graph, calculate the initial velocity and the height to which the object rises. Well, the initial velocity is at time equals 0, isn't it? Its VI is there. And this point over here is V final just for this piece. You with me? I'm glad you are. It's not a big deal, but now we say, okay, well, that's wonderful. We've got a VF is 0, VI we don't know, and we've got time of 2.5. So if we just look at our formulas, okay, remember one way to say is we've got VI, we don't know. VF is equal to 0. We know time is equal to 2.5. Acceleration and displacement, well, currently we don't know those. But here's where the trick comes in. They tell you, and we'll see it in another one, they tell you that it was launched, okay? We assume that it was launched on Earth, right? For all intents and purposes, we're not into the world of astrophysics here. We're talking about Earth. So what do we say? We say quite simply that it was launched on Earth. Therefore, the acceleration is G. Gravity, which means if it is launched, okay, and they say it is launched vertically upwards, what would G be? G in this case is minus 9.8 meters per second. That is the trick they're trying to get you to see. Otherwise, this is insoluble, isn't it? You've got 1, 2, you've got 3 unknowns, right? So, however, now we know that. Therefore, we say to ourselves, hang on. Remember, number 1, on a VT graph, right, on a VT graph, the slope equals acceleration. Therefore, delta V over delta T is equal to A. And we know delta V over delta T is 2.5 is equal to minus 9.8. Correct? All right. Therefore, delta V must be equal to minus 9.8 times 2.5. And in my calculator, that is minus 24.5. Delta V is always, in physics, V final minus V initial. Temperature final, temperature initial, etc., etc., etc. Okay? So what do we say now? We say, therefore, hang on, V final was 0. Minus VI is equal to minus 24.5. Therefore, VI is equal to 24.5 meters per second. Please excuse me if I do sometimes forget to write the units in these behind them. It's just one of those things I do, and or I don't do, actually, true. So we say, okay, 24.5 meters per second. So I can go back to my graph now and I can say, right, remember in physics when we're answering a question, we go back and you say, right, you are 24.5 meters per second. Now you say to yourself, all right, therefore the next part of the question was, how high did it rise? And we remember the second thing about a VT graph, the area under a velocity time graph is what? Equals delta x, the displacement. Right? The displacement. So how do I work it out? Well, the area equals delta x equals a half base times height. It's a triangle after all, which is a half times 2.5 times the height in this case is what? 24.5. Therefore, the displacement comes out to be 30.625 meters. Okay, and we have to answer it vertically upwards. All right. So we're saying to ourselves, just from the fact they told us it was launched vertically up, and they've given us a VT graph, we're able to answer the questions about it. Now, whenever you're given these graphs, I know, stuck record, here he goes. Remember, look at the axes, what you're given. And remember, displacement time graph or VT time graph give you different things. You need to look at the slopes, right? Because if you look at the slope of a displacement time graph, you're going to get velocity. Okay? Right, now let's have a look. Because it's dx or delta x over delta t, right? So now we say to ourselves, let's have a look. I've just drawn up a stock standard. Let me just get to a new page. I think it'd be better. I've drawn up a stock standard VT graph here. All right. Just bear with me a seckie while I draw it. And I'm saying that's to there. All right. And they say, right, you go to there. Then I've got it going further that way. Then I've got it coming down quite sharply like that to there. Then I've got it going along. And I've got it going back up. And you always run out of space to do that. Okay. And I am going to say A, B, C, D, E, F, G, and H. All right, so let us call this time H. This is time at A, which is 0, time at B, and C, D, etc. I don't want to write it in because I'm going to get myself into, not a mess, but I'm going to make a mess of my diagram. I don't want too much detail on here. The first question they say is describe, hang on Kevin, you haven't finished here. Okay, get away from that. This is velocity minus, plus, and time. Right. So they say, the question they ask is describe the motion. How do we start with these? Well, we first of all, when we say, okay, at A, it's time naught. That's the beginning. So this is VI here. Therefore, VF is at that point. So when we're dealing with time A to B, we only look at the information between A and B. We're not interested what went before A or after. It's between A and B only, right? The same for all of these kind of graphs, right? Now, the next one is to say to yourself, okay, now when I move to there, I say, well, this is now VI and this is VF. VI, VF, correct? VI, VF. VI, VF, right? Remember, it could be displacement instead of velocity. If it was displacement time graph, V initial, V final, V initial, V final. And please take note that at these particular points, this is equal to 0, equals 0, equals 0. Right? They've told you that at that point it's 0. So let us describe the motion between A and B. We say split it up. We say A to B. That's my way of doing it, A to B. So next I say, right, look at the velocity. Can you see V initial equals V final? V initial, V final, they are equal. What does that mean? It means that the velocity of my hurricane over here is the same here and the same there. Therefore, it means acceleration is 0. There is no acceleration. Thus, it is at constant velocity. I could also have looked at the slope of the line. So if we say, right, we do that, or look at slope. What is the slope? The slope is horizontal. Okay? Therefore, the gradient m is naught. If the gradient is naught, it means there's no acceleration, because the gradient is equal to delta v over delta t, which is equal to acceleration. Correct? See that? So what have we got here now? We say, okay, what's the next thing I can say? The next thing I've got to do is say, right, then I say, right, what is my displacement during that time? So from A to B, you'll say that it's at constant velocity, there's no acceleration, and the displacement during that period of time, displacement is equal to the area, which in this case, it's a rectangle, so it's going to be VI times time. All right? Because just look here, velocity is equal to distance, displacement over time. Therefore, velocity times time is equal to displacement. There it is. The area is the displacement, right? Just by doing that unit balance. Easy, brilliant way of doing it. And something that you'll do when we start looking at A-level or university physics. There's a lot of that kind of stuff that comes in. It's really cool. Okay, now, let's have a look from B to C, shall we? Okay, if you look at your graph, mine has gone on off screen. B to C. Oh, sorry, my bad. Just before I move away from this, when we then go and we write in the displacement over here. Okay? So displacement, we'll put a number. Say it's 10. Okay? And we will go and we'll put displacement here. Right? Etc. Already before we go any further, what about down here? These are negative displacements. These are positive displacements over here. You're going to get a positive answer when you work out that thingy. Let's have a look at the next one. All right? Just bear with me. We are going to do one, but I just want you to see it. B to C. I say, okay, now I can see that V final is greater than V initial. Therefore, delta V is going to be positive because VF minus V initial is greater than 0, isn't it? Okay? I hope this is not fading on the recording. I don't think it should be. It's just because it keeps losing my eyes. But anyway, never mind. Okay, it's wonderful technology actually, isn't it? So we say, okay, therefore it's positive. What does that mean? It means that I have gotten acceleration. There's an acceleration over there. And the acceleration is positive, right? So therefore I'm going to get delta V over delta T is going to be positive. It's going to be a positive number, which means that it is accelerating away from me, right? Away from the origin. It's accelerating away from the origin, okay? That's pretty important that we've got that sorted. So now what's our next situation? The next thing we've got to say is, okay, what is the displacement over that piece of time B to C? Well, displacement, whoops, I always do that. The displacement here is going to be the area, which in this case, it is a trapezium, right? And can you remember the formula for that? Yep. Wish I heard everybody say that, but I'm hoping you did. It's a half of the sum of the parallel sides times the perpendicular distance between. Okay? which is going to be equal to a half of sum of the parallel sides, VF plus VI over 2, right, times time. All right? Half the sum of the parallel sides times the perpendicular. And we go back and we write it on. Okay? So basically, that's going to be that. And that's positive, right? So it's a positive displacement. You are going to get to the point where the negative displacements, okay? Now, what do? We say to ourselves, all right, that doesn't matter. We're not really bothered about that. What do we do at the end is we say, if they say to us, where is the object relative to the origin? What have we done? We were traveling, here's the origin, constant velocity, then we accelerated, then we constant, then we slowed down, but then when we've gone, our velocity at that point over here, let me give you the name, at point E, between point D and E, right? Let's have a look here. Between D and E, okay? V final is now equal to naught. So therefore, delta V is going to be V final minus V initial, correct? Which is then going to be what? It's going to be V final minus V initial is going to be equal to 0 minus VI. All right? Which means I have got a negative acceleration. And a negative acceleration means what? Negative acceleration means that I am slowing down. But now I'm slowing down, can you see that? Now my velocity is 0. Now my velocity goes negative. What is that saying? It is saying that my car has turned around and it is coming back at me. So the negative displacement is the car is stopped here. Now it's coming backwards. I'm here. We started here, remember? So now the car is coming that way, right? Isn't it? So what is the final displacement relative to the origin? You simply add up the displacements. Okay? So you've got plus, 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 minus, 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 and you might end up with a delta x equal to minus 20 meters, which means that the vehicle is 20 meters this side of where we started. That's simple. It's not a big issue. It's just take the logic and look at what the vehicle is doing. All right? That is how we're going to answer these problems. Let us look at a bouncing object. Okay, let me get out my bouncer here. Okay, here's my blue ball. Right now, here's the blue ball. Okay, there it goes. Let us examine this motion a little bit slower. Let's put a freeze frame on it, shall we? So I drop it and it hits the deck. Right, here we go. Dropped, it's accelerating downwards, it's increasing its velocity until it hits the deck, right? Now what happens over here when I hit the deck? Well, there's a little time because essentially this ball flattens and bounces back. If you take a slow motion camera and take a picture of a squash ball, remember it's hollow inside? What happens is it's coming at the wall and it hits the wall there and it takes time to squeeze and to reverse the direction of motion is not instantaneous. It is not possible to have it instantaneous. It takes a split second of time. Where have we seen the split second before? Hold on, let me think. Momentum, impulse. This split second on the graph, some of them show it and in some books they don't use it. But let's do it properly. That delta t, okay, is an instant in time when it takes the ball to compress. So actually, if I look at a bouncing object, right? Let me take my bouncing object over here. Okay, I've got my page, so let me just draw, whoops. One day I'll learn not to do that, hey? Okay, let's just take over here displacement versus time graph. Okay, delta x. So delta x is plus and minus, right? Now, because it's bouncing, in this case, there's not going to be a negative because it's not going below the ground, right? So essentially, that's the ground. So let's have a look. Now what happened, okay? My displacement, okay, initially, what happened was the displacement was up, okay? And then what happened, okay? The displacement depends. If let's say I throw the ball up, okay? Let us say I throw it up, all right? Just so that it works nicely. There's my ball coming, and there it hits the ground. So over here, this is the maximum height, right? This is negative delta x. We don't have to worry about this is time. Now, at this point here, it's hit the ground. Now, technically, there's a little delta t over there because this ball then does that, doesn't it? Okay, that ball does that, right? Then what do I have to do? Then I've got another little delta t over here. All right, until my ball does this. Okay, can you see I threw the ball up? Right. Now let's draw the velocity time graph of this bouncing object, shall we? All right. This is plus v minus v. Okay, right. So at the initial point at time naught, what did we say? We said always look at the time intervals. Let's draw it in red. This is at time naught. Where am I? At time naught, I am above the ground and I went up. Therefore, at this point in time, okay, that's the maximum height, which corresponds to the velocity equal to 0 at that point. It's my turning point. There we go. Boom. Okay, it's the turning point, isn't it? So I say, okay, cool. Now I just want to drop my little lines down here again. Look here. Now over here, this one continues down, right? And the slope of that line is constant. It's the same. It is acceleration. Gravity, right? Because gravity stopped me, now it's accelerating me. But now what happens, okay? Now essentially I've got a little delta t because then my ball starts going up and it goes up with a new velocity going up, right? So I have that situation there, right? And then we have the same again. Let's have a look here. Okay, going down. Okay, and here's my little delta t over there again. Okay, can you see? And then I start bouncing up with a lesser velocity. And once again, bang, down we go like that, right? So these little delta t's here, okay, there and there, those are my bounces. Okay, so now let's draw an acceleration time graph, shall we? Let's go the whole hog. Why not? Just want to check that I'm back on the correct color. Okay, just to keep our axes going. And let's draw an acceleration time graph. This is plus a, minus a down here. Okay, now I throw the ball up. Up means which way is a? A is negative. So up to that point there, let's do this one in green. Okay, up to this one there. This acceleration must be minus 9.8, right? Then it's going to switch to plus 9.8 to there, correct? Then when it's going back up on that one, on the delta t, all right, let me just bring my little delta t, okay, down over there. And then it's going to switch again to minus, plus, right? Like that. Can you see? All right. So in all cases, my acceleration is going to reverse over the delta x as well, isn't it? Now, it might sound a little sort of complex at this stage, but we actually have to get down and do one, all right? What I'm going to do is I'm going to just, I'm going to stop this video slightly shorter than normal, and then I'm going to do a full-on example. There's quite a few, it's two objects passing each other, okay? Now, remember when we do these, I know, I keep saying it, look which kind of thing it is. Put in what you know. Watch out for the fact that if it's under gravity, they won't give you the slope, all right? doesn't matter which curve you start with. Always your time sections are the important pieces. So that you split it up in increments of time. That allows you to get a velocity or a displacement initial, a displacement final, and then calculate everything from there. Okay, dokes, I'll cut this one and then we'll go on and we'll look at an example. It's basically two objects passing. I'm going to do it conventional way, just to recap that, and then I'm going to do it using graphs of motion. Cheers, I'll see you straight after this.